Hello and happy Friday. Sorry that I am not at school today. I flew to Texas last night to spend the weekend with my family, but I knew that we needed to move on today to section 2.4 to learn about the chain rule. So earlier this week, I put together this video for you. So this video is going to walk you through some guided notes where we're going to discover what the chain rule is. We'll do some example problems where we have to use the chain rule. I'll give you some to try on your own, and hopefully by the end of class, you'll be feeling like an expert when it comes to using the chain rule. So let's get started. First thing we need to kind of talk about is what is the chain rule used for? So the chain rule tells us how to take the derivative of a composition. Now, we've seen compositions of functions back since Algebra 2, but just to give yourself a little reminder of maybe what compositions look like, maybe something like x plus 1 cubed. That is a composition because I have a function within another function. My function x plus 1 I would consider to be my inner function, and then something cubed would be my outer function. We often see compositions with roots, whether it's a square root, a cube root. Okay, so maybe I have something like the square root of 2x minus 3. So this is also a composition where, again, my inner function is 2x minus 3. My outer function is the radical. If I wanted to rewrite it, I would probably choose to use fractional exponents because then I could go about using the power rule. And we'll come do some of those later today. We can also see compositions with trigonometric functions. So maybe something like cosine of 2x. For cosine of 2x, my inner function is 2x. My outer function is cosine, so I'm taking the cosine of my inner function. We could also see it with trig functions that are maybe being raised to a power. So maybe something like tan squared. Now, if we see trigonometric functions being raised to a power, I'm probably going to encourage us to rewrite it before we take our derivative as the trigonometric function all raised to the power. These expressions are the same, but this helps us identify the inner function is tangent and the outer function is the squared. All right, so let's actually go ahead and write down what the chain rule is. So the chain rule tells us how do we take the derivative of a composition. So for my composition, I'm going to call it f of g of x. So g of x is my inner function. F of x is my outer function. So when I go take the derivative, chain rule says I'm going to take the derivative of the outer function. I'm going to keep the inner function exactly what it was, times, now I get to go multiply by the derivative of the inner function. So if you want to make yourself some notes, we're doing the derivative of the outer function, recognizing that the inner function was the same. We didn't change it. And then we multiplied by the derivative of the inner function. So it's going to be really important for us when we're using the chain rule to make sure that we can identify the outer and the inner functions. And I wrote you this little note here, and I'll explain what I mean. Imagine that you're opening a present. So this is what my high school calculus teacher taught me when it came to the chain rule. So if I have a present, I don't know, maybe it's a toy. Usually that toy is wrapped in a box. Usually that box maybe has some wrapping paper. And then maybe, I don't know, there's a bow on the top. So if I want to unwrap this present and I want to get to the toy inside, the first thing I have to do is undo the most outer layer, which is probably the bow. Now, as soon as I untie the bow, notice the toy is still inside the box. The wrapping paper is still on the box. So that inner function, my toy, my wrapping paper, everything stayed the same while I undid the bow. Then probably the next thing I would try is, can I rip off the packaging or the wrapping paper? When I rip off the packaging, remember, the toy is still inside. So every time you take a derivative and you do an outer layer, the inner function remains the same. All right, so now that we kind of have an idea of how the chain rule works, let's go ahead and do a couple example problems together. So the first one, this is a pretty simple power function. So we have a composition, it's being raised to the third power. So the third power is my outermost function. So chain rule says I need to go take the derivative of my outer function. Well, because the outer function is a cube, the 3 is going to come down. I'm going to do the power rule. And then notice that everything that was inside that function needs to stay the same. So my inner function that was x squared plus 1 is still inside. Times, now I get to go do the derivative of my inner function, which was 2x. So ultimately, I would simplify it and I would call it 6x times x squared plus 1 squared. Way easier to find the derivative this way than how we would have had to do it last week, which is expanding using the binomial theorem and Pascal's triangle. All right, I'm going to give you a chance to try example 2. So, Mr. Rude, if you would pause the video and give students a minute or two to try it on their own, and then have them come back and see how they did. All right, so let's check and see how you did. So because I was asked to find f prime, I would check your work and make sure that you have f prime equals. My outermost function is the fourth power, so the fourth power comes down. I do power rule. Everything inside is going to stay the same. Right, that's my inner function. Times, now I get to multiply by the derivative of the inner function, which was 3 minus 4x. And then probably I would simplify this a little, like I can multiply 4 by 3 minus 4x, and I would call it 12 minus 16x times 3x minus 2x squared cubed. There's no point in expanding this. This is how I'm going to leave it. All right, so now we are going to move on to one that's a little more challenging. So this one says, can we find the x-coordinate where the tangent line to the curve is horizontal? So we're not just finding the derivative. Now we want to know, when does that derivative have a slope of 0? So I'm going to make a note. The tangent line being horizontal means the slope is 0. So if I want to know where the slope is 0, I probably need to find the derivative and set it equal to 0. Now because I see a root, the first thing I'm going to do before I start taking derivatives is I'm going to rewrite this with fractional exponents so that then I can go do the power rule. Okay, we always want to do this when we see radicals. So let's go try the product rule. Right, this is a product because we have x squared times this other function. So the derivative of x squared is 2x times this piece stayed what it was plus x squared times, this is where we get to do chain rule. So the 1/2 comes down to the front. Everything inside is going to stay the same while I finish out power rule. So I get a negative 1/2 times the derivative of that inside, which was negative 2x. All right. So from this point, we found the derivative. If we're going to try to figure out where it's 0, we probably want to simplify and we want to factor. One of the best resources for us is that zero product property that we learned about back in Algebra 1. That zero product property tells us if we have a product that's multiplied to 0, one of those pieces has to be 0. So I'm going to try to use that, and I'm going to do it by factoring. So maybe the first thing that I notice is, okay, this second piece has a 1/2 and a 2. So I'm going to get rid of those. I think that's about the most I could simplify. I'll eventually call this x cubed, but for now I'm just going to leave it. And I'm going to start trying to factor out things that are in common between, let's see if I can get another color here, between this first piece and between the second piece, right? What is in common that I can factor out between them? So from the first piece, I noticed that I have an x. Over here I have an x, so I could definitely factor out an x. I also see that I have this 1 minus x squared in both pieces. They have different exponents, but they both have that same base. So when I factor it out, we saw this earlier in the week, I'm going to take it out to the most negative exponent. This is always going to leave me with positive exponents in the end. Okay, so let's keep going. That's what we've decided to factor out because it was the most negative. From the first piece, I have a 2 left over. I also have a 1 minus x squared left over, and I know that I have one of those because if I distribute this back in, just to kind of check my work, I know that when I have common bases, I add the exponents together, so when I add them, I get a 1/2. If I look at my second piece, well, let's see, I've got a negative. I took out 1x, so I definitely have an x squared here, and then I took out this whole piece, so I think all I have is an x squared. Now let's just keep on going here. I'm going to rewrite this. So I like to put things with negative exponents in the denominator. So I know I have an x on top. I know that in the denominator I have 1 minus x squared to the 1/2. And then if I look at what's left over here, if I simplify this, well, this was really 2 minus 2x squared minus another x squared. So that's going to leave me with a negative 3x squared. And now I should be able to keep going. So when I go set this thing equal to 0, maybe we even factor, oops, I forgot about that 2. Sorry about that. Let me come back and get that. I had that 2, so I still have a plus 2. There we go. So now when I set this thing equal to 0, what I notice is that the denominator plays no role on when this equals 0. It only comes from the numerator. So I'm going to take my two pieces of the numerator. One of them is x. So maybe x is 0, but also maybe negative 3x squared plus 2 is 0. So if I continue solving this, well, there's one answer. My second one, I subtract 2. I divide both sides by 3. I take the square root, and I get plus or minus the square root of 2/3. And if we don't have a calculator, that's how we're going to leave our answer. So to find the x-coordinate where the tangent line to the curve was horizontal, I went through, I set my derivative equal to 0, and then I just solved. Okay, so there were 3 places where this tangent line to the curve was horizontal. All right, let's keep going. So flip over to the next page. So I'm going to leave example 4 for you to try. It is very similar to the problem that we just did, except it involves quotient rule. So Mr. Rood, if you would pause the video, give them a couple minutes to try it, and then we'll come back together and we will check it together. All right, hopefully you've had a minute to try the problem. So I'm going to go ahead and work it out up here and we can just check our work and see what we had. So I'm going to go do quotient rule, even though now I could do product rule because I could rewrite this function like x times x squared minus 4 to the negative 1/3. Because now that I know about compositions, I could do that. But I'm going to do quotient rule because we haven't seen one yet. All right, so let's just check our quotient rule. So I take the derivative of the top, it's 1, times the bottom, minus whatever was in the top, times the derivative of the bottom. So this is where chain rule comes into play. So you just check your work, see if you did everything the same as me, making sure to multiply by the derivative of the inside, all over the denominator squared. And here again, I get to do a little bit of factoring. So in the numerator, I'm going to factor out, let's see, an x squared minus 4 to the 1/3, the negative 2/3 power. I like to take out the one that is most negative. So when I look at what's left, this first piece, well, this first piece definitely has an x squared minus 4 left over. It's going to be to the first power. Oops. So for that first power, I know it is because if I go distribute it back in, I add my exponents, I would get a 1/3. Minus, I go look at the second piece. Well, in this second piece, I took out this one, so it's gone. If I look at what's left, I have a negative 2/3 x squared. It's still all being divided by x squared minus 4 to the 2/3. Because this top thing is an x squared minus 4 to the 2/3, I'm going to go put it in the bottom, and I'm going to make this thing become a 4/3. Right? If I have 2 that are both 2/3 in the denominator, I can add those exponents together. 2/3 plus 2/3 is 4/3. And now I can set it equal to 0. My denominator plays no role on this. If I multiply it to the other side, it's still 0. If I combine the numerator, I would end up getting 1/3 x squared minus 4. And now it's a baby algebra problem. We add 4 to both sides. We multiply both sides by 3. We take the square root. We get plus or minus the square root of 12, which we would call plus or minus 2√3. All right, this video is about to end, so Mr. Rood, go ahead and play the second one.